Hello, everyone. Welcome to the last session of the Discovery seminar talks today. My name is Ramona Augustin. I'm a postdoc at Space Telescope Science Institute, working with Molly Peoples and Jason Tomlinson, and I will be chairing today's session. For those who have not joined a previous session, the aim of this talk series is to showcase the work of postdocs at Space Telescope and the Johns Hopkins University. As you all surely know, early career researchers have been disproportionately impacted by the COVID-19 pandemic due to reduced travel and networking opportunities. With this talk series, we want to provide them a platform where they can show their results to an international audience of astronomers. With the world opening up, we hope that this will be less necessary soon, and so today we have the last scheduled session so far. We will have two talks today. Each will be 20 to 25 minutes long. At the end of each talk, please feel free to ask questions. You can use the raise hand button in BlueJeans. If you do that, then I will call your name and then you can ask your question. Or if you feel more comfortable, you can write your question in the chat and I will read it for you. So without further ado, our first speaker today is Logan Jones. Logan is originally from a small town in Arkansas and obtained his PhD from the University of Wisconsin-Madison in August 2021, where he worked with Amy Barger on high redshift starburst galaxies. He joined STScI in September 2021, where he's now working with Svea Hernandez and the Mingle Group to understand the flow of metals in nearby galaxies, especially as seen in the UV. Today he will tell us about Open SESAMME, an ultraviolet understanding of the integrated light of star clusters. Logan, please take it away.
Thanks, Ramona. Are my slides coming through fine? Perfect. Cool. Hi everyone. I'm Logan Jones. I've been working here at STScI for coming up on a year now, working with the Metals in Galaxies group, Mingle, specifically with Dr. Svea Hernandez, who I think is in the call. And so today I want to present on a program that I've been working on for most of this past year, which I'm calling SESAMME, which is a tool for understanding the integrated light of star clusters in relatively nearby galaxies. So we're all pretty familiar with the periodic table. We have, metals, semi-metals, noble gases, etc. But at some point, yesterday's astronomers decided this was too much, so we're just going to chop it back down to this. We have hydrogen, helium, and then everything else. This itself is, of course, a bit of an oversimplification because there actually is stuff that you can glean by looking at all of this everything else individually. The various heavy elements all have different origins. For example, a lot of them come from various types of supernovae. Others come from merging neutron stars or other like winds of other dying stars. And so understanding where these elements come from and how they kind of get sloshed around within galaxies is an important way of understanding how galaxies came to be the way they are. And even though metals comprise maybe like at most about 1% of all baryonic mass, they are a major driver of a lot of the most interesting parts of astrophysics. In the interstellar medium, metals enable the gas to cool very efficiently via various collisional transitions, which cool gas then encourages new episodes of star formation. To build up interstellar dust, you need metals. And as kind of an observational bonus, metals make it much easier to determine redshifts via spectroscopy of various metal transitions. In stars, the amount of metals that you have in stars determines not only the strength of their ionizing output, which is a very salient question now that James Webb is up and running, but also the strength of their stellar winds. The chemical composition of stars also kind of includes the memory, like the fingerprint of the parent molecular gas cloud that they formed from, and so by looking at the metal content of stars, you can understand the past stellar generations that have came before it. And it's mostly this it's mostly this kind of like cycle of metals from cool gas to cold gas to stars and back again that I'm interested in understanding. Understanding that flow, that cycle between the stars, the ionized gas, and the neutral gas, helps to explain a lot of various like outstanding problems in astrophysics. It's kind of the root problem, understanding where these global metallicity relations come from. So for example, the mass metallicity relationship that's been seen in other galaxies. The origin of metallicity gradients in both gas and stars. So for example, the metallicity is usually much higher in the core of a galaxy and then drops as you go out to the outskirts. Metals are a big part of various questions related to how gas flows into and out of galaxies, and overall just kind of a big player in determining the star formation histories of galaxies and also the timescales on which that gas gets kind of whisked and stirred back in to the next generations of stars. And specifically, looking at metal lines in stars and the gas in the ultraviolet is going to be especially salient. Again, now that James Webb is up and running, we need to be able to kind of anchor our understanding of what we're seeing in the high redshift universe by looking at the rest frame ultraviolet. And so the research I'm going to be presenting today focuses very heavily on far ultraviolet spectroscopy towards young massive clusters, YMCs. These spectra have a lot of different metal lines, including ones that are sensitive to the age of the stars. So for example, on the right, this is an image of just like of a particular young massive cluster in the galaxy M83. That kind of cyan dashed line is about 2.5 arc seconds in diameter. That's the aperture of an instrument called COS, which I'll be talking a lot about. And this blue and gray curve in this left-hand graphic shows the spectrum that you get out from COS after it's been resampled to a 1 angstrom resolution. And I've marked a lot of major spectroscopic features here. The blue part of the spectrum are things that actually do belong to the stars. Anything else that isn't necessarily part of the stars themselves, so the ISM lines, geocoronal lines, or just like detector features, those have been grayed out. And so by looking towards these stellar clusters in the far UV, you can not only get a handle on the age and metal content of the stars, but also a handle on the metal content of the neutral gas via these ISM absorption features. And so beyond a few megaparsecs, these like young massive clusters are basically point sources, which means they fit very comfortably again within this 2.5 arc second COS aperture. And also, unlike spectroscopy or spectroscopic observations of whole galaxies, individual star clusters are much easier to approximate as a simple stellar population for modeling purposes. The main draw of that being is that you can assume that they are chemically like basically all of the stars formed at the same time from the same parent cloud, which means they have the same chemical makeup. But in general, SSP modeling requires that you assume something about the age to measure the metallicity or vice versa. For example, there's a technique that's been in use for a little bit over a decade now from Soren Larsen and company that is based on the use of theoretical isochrones. So you assume an age from the literature to create a bunch of stellar atmosphere models from these theoretical isochrones. And then you combine these models in a realistic way to create a synthetic spectrum of a star cluster, and then compare that with real data using just a basic like chi-squared minimization. So that That technique that technique was originally developed for kind of older star clusters and in the optical and with very high spectral resolution data. But since it's been developed, it has been extended down to kind of more modest spectral resolution and also down to UV wavelengths. And it's useful because you can not only measure the overall metallicity, which is symbolized by Z, but also the abundances of individual elements. Um, but a common problem with modeling these stellar populations is that in general there will be degeneracies between the age, the metallicity, and the reddening along the line of sight to that star cluster. And that means the results that you get out for the metallicity are going to depend on the age that you assume. And so ideally what you would want is to be able to constrain all three of these parameters at once. You can probably guess where this is going. So this is what the code that I've been writing is trying to do. It is a Python code for simultaneous estimates of star cluster age, metallicity, mass, and extinction, which I'm abbreviating as SESAMME. And so instead of choosing basically one or two models as like the best fit, you use statistics to find out what models are probabilistic good matches to the data using Markov Chain Monte Carlo computations. And I have some backup slides for the end if we need to go back over, or for folks who are interested in like what that actually like looks like. Sorry. So to measure the stellar properties with SESAMME, you put in three things. You put in your science spectrum towards the star cluster. You put in a set of these simple stellar population models, these like templates, plus a nebular. So the current testing that we've been doing is with a model set called BPAS, which I'll explain that here in a minute. And also by default, our modeling includes a nebular continuum component, which actually does have a small but significant impact on the ages and metallicities that you recover for these star clusters. And then the statistical machinery from it comes from a Python package called MC, which is a particular implementation of Markov Chain Monte Carlo. So you put in these three things, and what you get out are posterior probability distributions for each parameter in your model, which in this case it's age, metallicity, an extinction value, and a flux axis like rescale parameter that can sometimes be translated into mass, and I'll explain what that means here in a minute. And basically what this means is that given the data and its uncertainties, how likely is it that a given population model is going to be a good fit? So a closer look at kind of each of these kind of inputs here. The testing and initial science applications that we're going to be using SESAMME for are going to be based on far ultraviolet spectra from COS. Specifically, the testing that I've been doing so far has used a couple clusters from M83, which has a supersolar in general a supersolar metallicity value, and then NGC 1313, which is about half solar. And so down here you can see, for example, this is a spectrum towards the young massive cluster M83-8. The pink spectrum in the background there is what the actual COS data looks like at its native resolution of 0.06 angstroms. But for the analysis that we've been doing, we've actually been binning this data up to 1 angstrom resolution for comparison with the BPAS models. And so, obviously, when you do that, you may lose a little bit of this like very nice you lose a bit of the spectral resolution, and so a lot of these lines may start to get blended together. But the upside to doing this binning is that now you have this beautiful signal to noise in the ultraviolet. So whereas before you would be getting a signal to noise per pixel of like 3 or 5. Now we're getting up into 30, 40, 50. The spectral models that we're using, so again, all of the testing and kind of initial applications we've been doing so far have been with BPAS, which stands for Binary Population and Spectral Synthesis. It is a set of stellar evolution models that includes the effect of binary stars, which has a relatively big impact in the far UV. Basically, each model for a fixed stellar age and fixed stellar metallicity includes a synthetic spectrum that goes all the way from the extreme UV to the far infrared for a star cluster of mass of a 1 million solar mass cluster. These models come in a 1 angstrom spectral resolution and a flux axis in units of basically the solar luminosity. And so these are just 4 kind of examples of this. So we have in blue, yellow, and red 3 different populations of about solar or slightly higher than solar metallicity at 1 megayear, 3 megayear, and 10 megayear in age. And I've marked kind of very like major stellar lines here. So carbon, nitrogen, silicon, so on. And you can see as the age goes down, not only does the overall continuum normalization drop, but also the strength of these various lines, these age-sensitive lines, changes pretty rapidly with time. And then down here in purple, we have also a 10 megayear population, but at about 1/10 solar metallicity. And you can see that it's different enough from the high metallicity model that you can start to differentiate between metallicities and ages with enough signal to noise. And so even though this initial modeling is with BPAS, SESAMME itself is not exclusively based around BPAS. Pretty much any set of SSP models that you want can be put in, as long as it's made to follow the required formatting. So, for example, if you prefer Starburst 99, you can use Starburst 99. A quick kind of circle back to that flux rescaling parameter as well before we move on. So within BPAS, the mass normalization of these model SEDs means that this flux rescale parameter actually can be pretty much directly tied to the mass as long as the flux calibration of your science spectrum is, A, reliable, and B, in like physical units. If all you have is a relative flux calibration where the flux axis of your spectrum is, like the shape of it is correct, but the actual units are just kind of arbitrary, then that flux rescaling parameter is exactly that. It's just a way of making sure that these models, which are in solar luminosity units, can be made to match the spectrum. But if you have a flux calibration that is more absolute, then that parameter can effectively account for both distance and for mass, which means if you know the distance to your star cluster, you can also basically translate that parameter into an estimate of the mass. Although I will note that this has not really been a focus so far, especially as we're looking at these cost spectra. And so finally what you get out of MC is basically essentially plots like this. This is a corner plot, so just basically a way of displaying what the final posterior distributions of these 4 parameters are. And these 2 panels that have these blue vertical lines, these are comparison values from Fernandez 2019. This is for one of the clusters in M83. And you can see that in general, it tends to be, or SESAMME tends to prefer slightly younger ages and slightly lower metallicities than the literature does. So just a quick comparison as well to various clusters. So in NGC 1313, we're comparing the values that we get from SESAMME against those presented in STScI et al. 2022, which is based on which is part of the CLUES collaboration. In this work, they do basically a two population fit, and so the values in these these right three columns are a light-weighted average of those two populations. And we can see in general the ages and the reddening values are basically consistent. The metallicities that we're inferring with SESAMME are substantially lower than what they get from their modeling. And I think this may just be due to a resolution effect in BPAS. However, we've looked a lot more closely at M83, where the literature ages tend to be a little bit higher than what we recover with SESAMME, although these are based on photometry. So, for example, this first cluster here, M83-3, the age is basically consistent, although the metallicity is quite a bit lower. This M83-8, which is located kind of on the outskirts of M83, the age is much lower, but the metallicity is consistent. And again, I think this has to do with a combination of a difference in how the ages are being measured. For Hernandez 2019, these age values are from photometry. And so just to take a closer look at these M83 clusters. So this is just kind of like a broad view of the combined spectrum for M83-3. Again, in blue and gray, we have the real spectrum, and then the parameter or the model corresponding to the peaks in these different histograms here is shown in yellow, with some major spectral features kind of marked. And the overall shape of the model versus the real data is pretty consistent. But once we zoom in, we can start to see how well it actually does at reproducing these stellar parameters. So, for example, zooming into these silicon-4 and carbon-4 lines at about like 1400 and 1550 angstroms. Again, the gray parts here are ISM, belong to the ISM, and so they're not actually part of the fit. So in general, the model seems to do a pretty decent job at recovering the spectral profile of the C4 and the S4 and the silicon 4. However, when we go over to nitrogen 5, which is another age-sensitive line, we can see something kind of strange is happening. So in the real data, which again is in blue, there's a very clear dip down and then a jump up, almost like an EKG, kind of signature. While the best fit model is basically flat across this wavelength range. And so,
you have 5 minutes.
Oh, thank you. Nitrogen 5 usually has a very P Cygni-like spectral profile in very young clusters, and I mean young as in 1 to 3 megayears max. But in something about the way that they treat this line in BPAS means that at high metallicity, that P Cygni profile is very, very weak, even by 2 megayear. And that's kind of what this figure is supposed to show. So the blue and the orange are from Starburst 99 at an age of 2.5 megayear. And you can see it's a very clear dip down followed by a rise up, which is a very classic P Cygni profile. In red and green, so the green is a lower metallicity model. There's still a bit of a dip down followed by that jump up. So it's still, I would say, a pretty clear P Cygni profile. But then at higher metallicities, kind of what we're seeing in M83, that P Cygni profile is very wimpy. And so given the fact that we're seeing such a prominent P Cygni profile in the real data, even though our algorithm is preferring a very young and a very metal-rich model, what does this actually mean for us? Does it mean that is the algorithm latching on to the wrong metallicity, as in is the real stellar metallicity lower? is the cluster younger than what the algorithm thinks it is, or is this or is this nitrogen 5 coming from other places like a nebular contribution? We're not sure yet, but the posterior distributions themselves and also just visual inspection of the fits from other lines disfavors the idea that it's a lower metallicity or a younger age. So just a quick summary, I guess, in my last few minutes here. SESAMME is a Python code for assumption-free, simultaneous measurements of star cluster ages, metallicities, extinctions along the line of sight, and sometimes the mass. It's generally pretty good at inferring ages and reddening values that are consistent with the literature for both super and subsolar metallicity galaxies, and it's also flexible enough that you can swap out your model suite of choice, which is good for not only taking advantage of the different spectral resolutions, but also, as we just saw, looking in very close detail at the differences in how well different models reproduce specific features. For example, the nitrogen 5, or a similar exercise that was done in a paper by John Chisholm and company in 2019 for Silicon 4. And so as for the future, what we're going to do with this code, once we continue to understand how it's actually, or like what it's, or like to understand its limitations and its strengths, we have 16 star clusters with COS spectroscopy just in M83, and then also archival COS spectra for young massive clusters in many, many galaxies that span different various types, masses, metallicities, star formation rates, and so on. So, for example, these middle two here, these are both very low metallicity galaxies, DDO68 and one's Wiki 18. On the far left here, we have, I think this is NGC 3125, which is kind of LMC or SMC-like metallicity, and then of course M83 here on the far right. All of these galaxies have literature measurements of their neutral gas, their ionized gas, and sometimes even their molecular gas properties, their metallicities, their abundances, their dynamics. Once we measure the stellar properties of these things, we can start to convert these different metallicity diagnostics and get a handle on the timescales of how this material flows between the stellar phase and the various gas phases, as well as the differences in the metallicity relations between these phases. And again, understanding how these relations arise and how these differences in the metallicity relations and gradients arise is going to be very important to enhance the science productivity of James Webb. And I think with that, we're about out of time. So I'm happy to take some questions.
Very much, Logan. That was a very interesting talk. We have one question in the chat. That's from Ian. He says, typically, how long does it take to run SESAMME for one star cluster? Is it parallelized?
It is currently not parallelized, but that is something that I'm trying to work on getting to work. For running it just like on my personal laptop, a chain of about 1,000 steps takes about 10 minutes. I'm sure if you were to move that up to a bigger computer, it would go a lot faster.
Okay. And then Jason has a question.
Oh, actually, I think there's one more as well from Kate.
Yes, I've forwarded the time. Can you maybe just answer that in the chat later?
Oh, sure, of course. Go ahead, Jason.
My question is about the mass estimates. To varying degrees, these clusters are going to be resolved objects within the COS aperture, and in some cases, they might actually fill the COS aperture. So I wonder how much of an effect that has on your mass estimates when you get them.
That's not something that we've thought too much about quite yet, especially since I mean what I was taught as a student as well is that trying to get a mass estimate from specifically from just UV observations is kind of rough to begin with because you're only sensitive to you know, a handful of the most massive stars, whereas all the mass is in the lower mass stars. So I'm actually not quite sure yet what effect that would have. So not sure if that helps at all, but
Okay, great. Thanks again very much, Logan. And if you have any further questions, put them in the chat and Logan will answer them there. But we will move on now to our second speaker today, which is Isabel Rebollido. Isa did her master's at the University of La Laguna in Tenerife, Spain. After that, she spent a year as a research trainee at ESA in Madrid. She obtained her PhD in 2020 at the University Autónoma de Madrid under the supervision of Eva Villaverde and Benjamin Montesinos. She joined STScI in September 2020, where she works with Marshall Perrin and Christine Chen in several projects that study debris disks and the circumstellar environment of main sequence stars. Today she will tell us about observations of the Beta Pictoris disk with HST. Isa, the floor is yours.
Thank you so much, Ramona. Can you just confirm if you can see my slides? I can't hear you. I can see you.
I can see the slides.
Okay. Thank you so much. Yeah, thank you, Ramona, for the introduction. Sorry for the technical issues. I'm not sure which screen I'm sharing. So yeah, as Ramona said, I'm going to talk about the project that I'm working on here at Space Telescope about a study of Beta Pictoris, which is a very famous debris disk from space, using HST data, which will work as a preliminary work for the upcoming James Webb data that we will be having in just a few months. So in order to talk about Beta Pic, I would like to start from the basics, just because I know a lot of people are joining just to hear Logan's talk, so maybe you're not super familiar with what a debris disk is. So a debris disk is just like one of the final stages of the planet formation process, stellar and planet formation process. This is a very nice diagram that shows how the protoplanetary phase evolves from A to D. We start after the formation of the star with a very hot energetic star that it's pre-main sequence yet, and the disk surrounding it, it's really, really big. It's very massive, but it's mostly composed of gas. And that gas is accreted onto the star, or sometimes it's photo-evaporated from the very high energy photons from the star. So the disk diminishes in mass as time goes on. And not only that, but there is also the angular momentum affecting that helps settle the disk. And a lot of low energy collisions between the smaller particles within. The temperature also lows, so some of the material that was in gaseous form solidifies. So we start to generate a lot of dust particles that will accrete onto each other and like just make them bigger and bigger until they reach like more or less the meter-sized bodies. And the gas continues to evaporate. The material continues to settle, and at some point a gap is open, and most of the gas is clear from the disk. So we end up with what we call a debris disk, which is just circumstellar material, but instead of what we had at the beginning, which was a lot of gas, now we have basically no gas, but a lot of dust. We know that this dust should be replenished as well, like it should be eliminated from the disk as the material coagulates and grows. But that's not what we see. What we see is that there is still a lot of dust, even thousands of years after models predict the dust to be depleted, which means that there is a lot of dynamical activity in the disk still, that it's generating collisions, which lead to dust production. And these collisions, they also produce a very small amount of gas. So when we are at the debris disk stage, we have a lot of dust in the disk. We have very minimal amounts of gas that it's also being replenished from collisions and evaporation. But we can already have some large planetesimals of protoplanets and even some planets. So we do expect to find planets that have formed along the protoplanetary phase in debris disks. So this is basically the concept of debris disk. So you maybe agree with me that they are interesting because it's the first stages of planet formation, of mature planetary systems, let's say. The star is already in the main sequence. And classically, these have been the 4 most famous debris disks. We have other targets now that are interesting for different reasons, but these were the Fantastic Four at the beginning of these studies. First, because they are bright, and second, because they are close, so they're easy to study. You have here Beta Peak, Fomalhaut, Epsilon, Eridani, and Vega. Those are the Fantastic Four. And you can see here as well that we can see them in very different wavelengths. We can see them in the optical, in the far infrared, and in the submillimetric and millimetric from ALMA as well, but also in the near infrared. And there is a lot of dust that is scattering light from the star. So if the disks are bright and they are big, we can observe a lot of stuff in them. So this doesn't come as a surprise anymore, I think. I'm going to talk about Beta Peak. This is one of the most interesting debris disks still. It doesn't fall into the Fantastic Four category. Well, it falls in the Fantastic Four category, but it's not because of that it's still very studied, but it's because of its characteristics. Compared to these other 4 disks, it's very young. It's only 23 million years. So the depletion of the protoplanetary disks happen within around 10, 12, 15 million years. So this is just at the end of that, just a few million years after that. Whereas the other Fantastic Four disks, the other 3, are way, way older. So this gives us an insight on the first phases of the debris disk. It's also really close. It's only 19 parsecs away. It's an 8-2 type star, which means it's like 8,800 Kelvin, more or less. And it has a very high dust fractional luminosity, which is how we measure how bright the dust is compared to the star. So 10 to the minus 3 might not seem a lot, because that means it's 1,000 times less bright than the star. And when we compare it to protoplanetary disk, it's not bright, but when we compare it to other debris disk, it is. So these, the studies on Beta Peak started around the 1980s with IRAS, which was the first infrared mission in space, let's say a precursor of James Webb. And just IRAS found that there was an infrared excess that was not expected around the star Beta Pictoris, and scientists attributed it immediately to circumstellar material. So there must be a planetary system around the star Beta Pictoris. And just a year after, in a small telescope at 2.5 meters in Chile, Smith and Terrell found that it is extended and can be observed from ground. I believe this was 800 nanometers, 100 microns. Yeah, I can't remember, 100 nanometers. I can't remember exactly. But yeah, so it can be observed even from ground. This was in the 84. We have come a long way. We have better techniques. We understand imaging and coronagraphy better now. And we have some really amazing images from a lot of different telescopes, both on the ground and in space. This is the one that I chose to show here because I think it's very beautiful, and it's very illustrative of the distribution of the dust in the system. It's from Hubble Space Telescope, from the ACS instrument. It was published by David Golimowski in 2006. And they are both the same image, the top and the bottom, but the bottom shows specifically the components. You can see the occulting mask, you can see the location of the star, and you can see the primary and the secondary disk. So the disk is warped. We see that it's not completely restricted to a plane. And that warp was attributed to a secondary disk that is tilted with respect to the main one. It's less bright, it's smaller, but it's only tilted about like 5 degrees. And this was consistent for years with the presence of a gravitational perturber in the system. It could have been a binary, but some of the predictions suggested it was a planet, and it was eventually found, Beta Peak B, in 2008 by the team of Marie Lagrange, using the VLT telescope in Chile again. We have characterized this planet now pretty well. Again, this was 2008, some time has passed, and we have a lot of images of the planet around the star Beta Pictoris. I really like this animation where you can see how it transits the star. It's one of the few planets we have detected with imaging. You know, there's like 5,000 planets, or over 5,000 planets that we know around other stars, but not so many that we can actually see with direct imaging. So this is a very special candidate. It is shown here in the context of the rest of the debris disk. You see the debris disk is huge compared to the orbit of the planet. The planet orbits at like 9 astronomical units, which is way smaller than the size of Saturn orbits, which you can also see in this plot. So it's really, really close to a star. It's a giant planet. It's several Jupiter masses. And it's located in the very inner regions of the system. The disk is expected to stand over 1,000 astronomical units, closer to 2,000 astronomical units. And eventually, another planet was found in this case. It was also a Marie-Lagrange teams. In this case, it was found with radial velocities because we have been studying this planet for almost 40 years, this system for almost 40 years, and we have a lot of spectra. So even though it is hard to find planets around A-type stars with radial velocities, we had so much data that it was possible to find the hints of a planet being hidden there. And it's now beta Pictoris C, and it's even closer in to the star. So it's really hard to image this planet because it is so close. There has recently been a very interesting result from Cicero Liu, a student at Johns Hopkins, where she found that there is a change in the spatial, in the crystallinity and composition of the dust within the spatial distribution. So for longer distances from the star, the grains are more crystalline, so a different type of processing of the dust, and there is also different composition. So this is really nice because it's actually consistent with the location of the planet. So it means that the planet is possibly affecting how the dust is processed in the system and generating two different populations of dust, both inside and outside of the planet. And if you remember, I also told you that sometimes when there is collisions and evaporations, there is minimal amounts of gas in debris disks. And we can see it too in beta Pictoris. This is the case of what we see with ALMA. This is CO gas in millimetric regime. And they do not only see that there is gas, but they see a clump of gas. So the gas is asymmetric within the disk, which initially pointed towards like the presence of a planet, maybe clumping the gas around it, or a collision. But the truth is that right now we're not sure where the gas, where the clump comes from, but there are several studies going on. There is also gas that we can see when we look at the spectra. This is a calcium-2 line, and we see optical spectra that it's very stable, very close to the star, that you see at around 20 kilometers per second there. But there is also a lot of variable features that we see in the spectra, like we do in this video. You can see the red line changes with date that is shown at the top of the plot, and there is an average shown in black. And all these variations that we see in the spectra are actually exocomets that are transiting the star and evaporating. And these are the tails of the comets that we see when they evaporate and produce an absorption in the stellar spectra. And we have so many, and we also can see them when we study the photometric light curves, that we were able at this point to generate a statistical study of the population of small bodies around beta Pictoris. So this is the first system where we can say, well, this is the size range of the minor bodies. And turns out it is pretty consistent. You can see in the right side plot, it is pretty consistent with the size distribution we find in the solar system, which kind of makes sense, right? Because we expect them to be formed in a similar way. So this is a very thorough background on beta Pictoris. And this is what I'm doing now. I'm taking the images from arXiv and also from some unpublished work from beta Pictoris taken with HST. There is also some NICMOS data that I did not include because the quality and sensitivity was not as good as the other one, so it was introducing a lot of noise. I have these mainly 3 data sets from ACS. I showed you at the beginning the work by David Golimowski. I have 3 images from STIS that were published in Daniela Pai's paper in 2015. And one of them, it's also going to be published in Bin Ren's upcoming publication. It's almost ready to go. And then there is 2 wide-field camera 3 images on the 2 filters, 110 and 160. The 110 filter has already been published in Nick Ballering's work in 2016, where he made an amazing job of finding a model that fitted different wavelengths. And the other will hopefully be published soon in a work that I'm preparing with what I'm going to show you here. So we studied the disk for all the images by collapsing it with what we thought was the average or the significant height after doing some calculations, which is around 40 astronomical units. So we just collapsed the disk, and that gives us some background noise further from the star, but it also helps us average out the asymmetries within both sides. So these are the 2 profiles. We have the southwest side and the northeast side. Disk is slightly inclined with the north being up. So what we know already from previous works is that the southwest side is slightly brighter, and we can see it also here. It even has a different exponential decay, the brightness of the profile, but this was already known, so we were not surprised. We were also not surprised when we looked at the contrast, and we saw that the disk is brighter in longer wavelengths than the star. So the star decays with a black body, but the black body of the disk peaks actually closer to 100 microns. So it is brighter in the infrared, so that's also okay to check. But the most interesting part of the analysis that we are doing is this. We looked at the comparison between the southwest side and the northeast side. This is just a subtraction of the 2 profiles based on the distance from the star. And what we see is that there is an asymmetry that we already kind of knew about on the southwest side, where it's brighter with respect to the northeast side. But you can see also that the peak of the asymmetry seems to be located at different distances depending on the color. So the redder filters seem to have the peak closer to 100 astronomical units, but the bluer colors that are closer to visible wavelengths, ACS and STIS, peak closer to 70 astronomical units. So does this mean that the location of the asymmetry is wavelength dependent? Yeah, you can see there the 2 more or less estimated locations so far. But there is something on top of this that is, if you remember, there is a CO clump, there is a CO asymmetry we see in the gas that is constrained between 50 and 160 astronomical units, which kind of overlaps with what we see here, being the peak in the CO at 85 astronomical units. So within, like, kind of in the middle of the 2 asymmetries that we see. If you remember, like, this is the plot that I showed before, and the peak is, you can also see it there between like 50 and 100 and something astronomical units. So this is really interesting, but we need to check other wavelengths to see if this keeps happening, if the location of the peak changes, or if there is an asymmetry at all, because we don't know if we're going to find this for every wavelength. And some wavelengths that we're going to check in the near future are the ones that are seen from James Webb. We will be doing chronographic observations of beta peak with NIRCam and MIRI with the GTO program 1411. The observations will be taken in December, so we expect to spend this time from now until then getting ready to reduce them and analyze them as quickly as possible, and maybe check these asymmetries. If we're lucky, we can see them. Something that we have also been doing, trying to prepare for James Webb data, is some modeling, where we are taking, you can see in the left side, the spectra of the star, and then the spectral energy distribution as well of the photometry of the disk in the orange dots, and our model is the black line. And you see it doesn't fit very well. And so this is more like modeling attempts. We'll get there. We're just not getting to perfection yet. We are also having some problems when comparing the disk planes, which is calculated for the model, the disk profile in the same way as we did for the images that I told you when we were averaging, collapsing 40 astronomical units, more or less. That's the height we expect. But we do not get yet the correct exponential profile. So we're still working on that. I can show you some pretty images of the models, how they look next to our images from HST, but this is kind of tricky to compare because we don't have a chronograph in our models. We don't have any stellar subtraction. So they look brighter than the images, but I promise the fluxes, if we go back, the fluxes are actually kind of consistent. So I'm pretty confident the brightness is correct, even though here it's kind of tricky to look at. I think I'm doing well on time, so I'm just gonna take a second for the conclusions and the takeaway messages. So I wanted to convince you, and I hope I did, that BetaPic is one of the most interesting disks to study. Is one of the most studied disks already, and that's not just a coincidence. It is. It has everything. It has planets. It has dust. It has gas. It has exocomets. So it's a lot. It's super interesting, and there is a lot of stuff to look into. So it has 2 planets that have been discovered so far, but there might be more. And this is something I forgot to mention before, but and this apparently happens a lot in A-type stars, but the planet is misaligned with the disk. So it's not coplanar with the disk, which can also explain the misalignment of the secondary disk. It remains the only system where we have certainty of the presence of minor bodies. I do like a lot exocometary studies. If you know any of my research, like I have focused a lot on that. But BetaPic is the only one where we have seen them in photometry and the spectroscopy multiple times. Like there is a lot of minor bodies around BetaPic evaporating and generating features that we can actually trace. The disk has at least 2 misaligned components and a gaseous clamp, so it means the structure of the disk itself, it's really interesting. The geometry of the disk is really interesting. There is a lot of stuff going on that it's generating asymmetries and misalignments, and that on itself, regardless of the composition or the rest of the components, is interesting, right? And then we find the clamp as well when we look at optical and near-infrared wavelengths, but it seems to be a wavelength. The location of the clamp seems to be wavelength dependent, and this is something that we're going to look more into. As future work, we are still working on the modeling. We are still working on preparation for James Webb observations with simulations with NIRCam. There is a lot of packages online for simulations with James Webb. Let me know if you want to know who to contact. I might not be the person, but I can point you to them, both for NIRCam and MIRI. There is a program that is also going to look at the MRS spectra, result spectra. So it's going to actually give us information about the composition with spatial component of the disk. So that's also going to be really cool. And we hope to constrain a lot of properties of the disk with the data we get from James Webb, including composition, size, and distribution of the dust. And I'm going to leave this slide up. And thank you very much for your attention. And I'm happy to answer any questions.
Very much, Lisa. That was very interesting. Anyone has any question, please raise your hands or put your question in the chat. Nicole.
Hi, Isa. That was really great. It was nice to see the whole story of BetaPic, in addition to the nice animation with the planet. In your plots showing the collapsed flux versus the stellocentric distance, it looked like a couple of the STS filters had much steeper exponential decays. Are those tracing like very significantly different grain size distributions from the rest of the filters? I should remember the STS filters, but I don't. So
sorry, I was muted. I wanted to bring up the plot. So are we talking about this one?
Yeah, that one, yeah, with the one that's in teal and then the one that's in gold that have much deeper drop-offs.
Yeah, so this is the contrast with the star. So here what you're seeing is the brightness of the disk with respect to the brightness of the star. So what it's actually showing is that the difference in flux is less than with the infrared. So the disk is less bright at these wavelengths than at infrared wavelengths.
Okay, so is that tracing
Yeah, so
smaller?
that would actually be connected to both the flux distribution of the star and the flux distribution of the disk, right? So what we would be tracing would be less small dust. So the shorter the wavelength, the smaller the dust, right? So it would mean that there is less smaller grains.
Okay. Cool, thank you.
Sure.
Any other questions? Emily.
Hi, Isa. That was a really great talk. I noticed on your plot where you overlaid all of the velocities of the exocomets from the beta Pic system. They're all in like the positive velocity space. Is that expected, or is there a reason for that, or is it the asymmetry of the disk?
So that happens for every exocometary system, and we actually think this is just an observational bias, because what it means is that the comets are, so if they're redshifted, they are moving away from the line of sight, right? That means on the right side, it's the velocity space, so it's redshifted. So they're moving away from us. So that means they have already came close to the star, so they are not, I want to explain this, but it's kind of tricky. They're not coming into the star, they're going away from the star. So they have already started and going through the evaporation process. So if they're coming in, they might not be hot enough yet, but if they're going out, they already absorbed a lot of radiation and they are already evaporating away. So that's why we think there are, like, for every exocometary system, more redshifted events. But it depends on the distance to the star. So if they are really close, they can already be evaporating when they are still coming towards us and blue shifted. I don't know if that was clear.
Yeah, no, that's awesome. Thanks.
Any last question for Isa? If not, thanks again very much, Isa, and also Logan for the first talk.
Thank you.
And thank you for everyone for joining in for the last session of the Discovery Talks today. Bye.
Thank you for organizing. Bye-bye.
Thanks, everyone. Bye-bye.